All right, I want to start off talking about vector linear combinations. Linear combinations is a concept that is absolutely fundamental to linear algebra, and so it's important that we have a good understanding of what we mean when we say a linear combination. So linear combination is going to involve two operations: vector addition and scalar multiplication. Okay, so suppose we have two vectors, v1 and v2. And we want to express a linear combination of these two vectors. So a linear combination of v1 and v2 can be expressed as c v1 plus d times v2. Now in this expression, c and d are scalars. So again, we have scalars multiplying the vectors, and then we're adding those vectors together. Remember, scalar times a vector is a vector. Graphically, we can look at what's happening here. If this is our vector v1, and suppose this is our vector v2, when we add these vectors together, you can think of it as placing them tip to tail. So if we took v2, placed it tip to tail with v1, we get a resultant vector, and that is the sum of v1 plus v2. When we're scaling the vectors, for example, if this is our vector v1 and we scale it, say we're going to multiply it by some scalar c, let's say this c is 2, then we're lengthening this vector. So this would be 2v1. If it was scalar 1/2, then we would shorten it, and this would be 1/2 v1. And if we multiply it by a negative number, it's going to point in the opposite direction, so this would be minus v1. One thing to note is that all the scalar multiples of v1 lie along this line that extends out infinitely, but contains the origin and the point v1. In 3 dimensions, our vectors will have 3 components. So let's look at an example of that. If, for example, suppose we have a vector v1 now in 3 dimensions, so let's suppose v1 is this vector 1, 1, negative 1, and suppose the vector v2 is equal to a vector 1, 2, 3. Let's look at a linear combination of v1 and v2. Let's suppose we're going to do 5v1 plus 2v2. Okay, so now our scalars are 5 and 2. So here's how that goes. That's going to be 5 times this vector 1, 1, negative 1 plus 2 times the vector 1, 2, 3. And this is going to equal, first we'll do the scalar multiplication. So I have 5, 5, negative 5. And I have 2, 4, and 6. So that is going to equal the vector 7, 9, 1. Whether we do the operations like this or graphically, it's really the same thing. You can just think of this point 1, 1, negative 1 as the point where that arrow would be in 3-dimensional space. So just to take that back down into 2 dimensions, if we're looking at the vector 1, 2 written like that, and we've got 1 and 2, so that vector ends there, and that's the vector 1, 2. You may also see that we will write these vectors slightly differently. You may see the vector written like this, and by convention we consider all vectors to be column vectors, so this is the same as the vector 1, 1, 1. You may just see it written like this because it takes up less space, especially in a textbook, but remember that our vectors are column vectors by convention. Okay, so there are some important things that we want to think about when we think about a vector, right? So suppose we have some vector u. We can think about what are all the linear combinations of the equation Cu. In other words, for all possible C, what does this look like? Another question that we can think about is, suppose we have two vectors, u and v. Then it's important to think about what are all the linear combinations of u and v. So what is Cu plus dv for all possible C and D? And we can, of course, extend this into 3 dimensions if we had 3 vectors. But let's think about this for now. Suppose I have 2 vectors, u and v, and I want to take all possible linear combinations of these vectors. So any possible C, any possible D, I multiply C and D times u and v, then I add those together and I put a dot. And the question is, after I do this for all possible C's and D's, what do I have? And for this case, I would have the plane, the R2 plane, right? Because every possible combination of this u with this v allows me to get anywhere in the plane. For example, suppose I wanted to get to this spot over here. Well, I can take, let's say, negative u, maybe plus, it looks like maybe plus 1.5 v might get me there. Maybe I need a little more u. So let's say negative 2u. And there we go. That would be about 1.5 v. Right, so for example, and I can get anywhere in the plane using this concept. On the other hand, if my 2 vectors were collinear, so for example, if this was u and this one was v, now linear combinations will only allow me to get on this line that passes through the origin and contains u and v. So a very much different answer to the question, what are all the possible combinations, linear combinations of u and v in that case? In one case they fill R2, in the other case they fill a line in R2. Okay, this brings us to the idea of the length of a vector. Which is closely related to the idea of a dot product. So we can probably figure out that if I have a vector, let's say the vector 1, 1, and I want to figure out how long that vector is, well, we can use trigonometry. We know that if I form the right triangle like this, that this side will be 1 and this side will be 1. So then I can use Pythagoras Theorem and say that you know, if I call this h for the hypotenuse, then h equals the square root of 1 squared plus 1 squared, which equals the square root of 2. And we can think about that if we looked at the vector in this form, then we can say, well, we just square each element of the vector and then add them together and take the square root. And that would be the same as taking the dot product of the vector with itself. So let's define the dot product very quick. Suppose we have two vectors, u and v. The dot product of those vectors we will define as u transpose v. So let's see an example. Suppose u is equal to the vector 1, 3, and suppose v is equal to the vector 2, negative 1. And I want to take the dot product u dot v, which we just said is equal to u transpose v. So I need to transpose this u, which means that I let the rows become the columns, or the columns become the rows. So that would simply look like this. 1, 3. Now I have a row vector. And 2 minus 1. And I do this multiplication. I do element-wise multiplication and then add the sums together. So this is 2 plus negative 3. So that's negative 1. Now let's go back to our example where we had that vector 1, 1, and we want to find the length of this vector. So I said if I take the dot product, the square root of the dot product of that vector with itself, so if I take the dot product of the vector with itself, this is going to be 1 plus 1 is 2. So let's suppose we say this is going to be the vector v1. So there is v1 dot v1. v1 dotted with itself. And if I want the length of v1, write it like that. Magnitude of v1, that equals the square root of v1 dotted with itself, which, as we can see up here, equals the square root of 2. And so we get the same answer as we did before. Another important thing to know is that the dot product of perpendicular vectors is always 0. An easy way to see this is if we look at, for example, suppose we're in the plane here. We consider this vector and this vector. So this is the vector 1, 0, and this is the vector 0, 1. So I have 1, 0 and 0, 1. And I'm going to take the dot product of these two vectors. So I'll take the transpose. And of course I have 1 times 0 is 0, plus 0 times 1, also 0, and this equals 0. Another example that may not be so obvious, suppose I have the vector 4, 2 dotted with negative 1, 2, and I want to know, are these perpendicular? Well, let's see. This is the first one transpose times the second one. This is going to be negative 4 plus 4, which equals 0. So these vectors are in fact perpendicular. Now, you probably know that matrix multiplication in general is not commutative, but dot products are commutative. So it is a fact that u dot v is equal to v dot u. Just want to make sure, I'll just write it again, this notation that I used up here, this means the length of v. and again found by the square root of the sum of the squares. Now this idea extends beyond 2 and 3 dimensions. So suppose we have the vector 1, 1, 2, 1, and we want to know the length of this vector. Well, we can just use the same method. So if I want the magnitude of this vector, use the terms magnitude and length synonymously. I take the dot product. Well, it's going to be the square root of the dot product. 1, 1, 2, 1 times 1, 1, 2, 1. And this is going to be 1 plus 1 is 2, plus 4 is 6, plus 1 is 7. So this is root 7. So no matter how large the vectors get, you can find length using this idea. Another important concept is the idea of a unit vector. So you probably know that vectors like 1, 0 and 0, 1, these are unit vectors. However, what if I wanted a unit vector that points in the direction of that vector? In other words, I want a vector that is length 1 that points in the direction of this vector. Well, that's pretty easy to do, because if I already know the length of this vector is root 7. So if I just divide the vector by its length, 1 over root 7 times 1, 1, 2, 1, this is a unit vector in the direction of this original vector 1, 1, 2, 1. If you like, you can put the root 7s inside. Or you can leave them out. You can rationalize if you want. So, in general, we can say that V divided by magnitude V is a unit vector in the direction of V. Okay, another important idea is being able to find the angle between two vectors. So let's say the angle between U and V. And the angle between U and V is going to be equal to, well, let me say it this way. Let's say the angle between U and V, let's call it theta. So the cosine of theta is equal to the dot product U dot V divided by magnitude U times magnitude V. So if you want to find the angle, you can just compute this expression and then take the inverse cosine. Now, there's a couple inequalities that always hold for vectors. I want to give you those as well. The first one that we'll talk about is called the Schwartz Inequality. And that says this: the absolute value of V dot U is less than or equal to the magnitude of V times the magnitude of U. This is an absolute value because remember, when you do this dot product V dot U, you're going to get a scalar. A scalar could be negative. We want to normalize it, so we take the absolute value. The second one I want to give you is called the Triangle Inequality. Triangle Inequality says the magnitude of v plus u is going to be less than or equal to the magnitude of v plus the magnitude of u. One way to think about this triangle inequality is if I've got two vectors and I add them together, and I can think about the length of those two vectors. So I've got some vector here and I add it to some vector here to get this resultant vector here, right? And that forms a triangle, which is why they call it the triangle inequality. So the best I can do, the longest this can get, is if v and u, the two vectors that I add, happen to go in the same direction, right? If this is v and this is u, and that's when I get the equal to, right? V plus u, this is the vector v plus u, its length is equal to the length of v plus the length of u. Any other situation, the resultant vector will always be shorter, less than the sum of the sum of the lengths of the two vectors.